Hey guys, GWS here to give you an introduction to the Q-Learning Corruptor that I have created. We're going to be using this on Star Fox this time. We won't be using it on Mario 64 because Star Fox you can actually see some interesting stuff that'll happen as a result of this. It's much harder to get anything out of the N64 because part of the problem there is you're dealing with a lot of coprocessor opcodes, and you're dealing with a lot of indirection, and you could train it, but it's a lot easier to train these things on direct interaction with the processor. So any kind of retro ROMs that you want to corrupt, this works the best for. Now it'll still corrupt for your N64. There'll be interesting things that you could see, but you're getting a lot more errors and it's a lot more work. So for this update, which I'm going to go through everything again and what it does, what's outdated, what's going to be coming out, and then when I get the final version of this out, we'll get an introduction. But this is more going to be just for kind of documentation purposes. So, how do you use the Q-Learning Corruptor? What is the Q-Learning Corruptor, first of all? The Q-Learning Corruptor uses machine learning, reinforcement learning, combined with aspects of genetic algorithms in order to produce interesting corruptions for your games. And while I have this designed for a particular training method, I also have more of an open design so that maybe people would have their own methods of training the AI to corrupt their games. So we're going to look at some new stuff that I've added. And a little bit of stuff under the hood we'll go over. So first of all, what you would do is, we've already got our game loaded here, but you just click load, and then it's important to realize that this is going to create, this will actually create two folders. This presentation one is a custom folder, but you're going to get a QTable folder and a branch folder. So it's important when you use this corruptor that you have your ROMs in their own separate folders, right? Make sure your ROM file is in its own unique folder, because otherwise it won't work right, because it'll be creating a folder in that same directory. I hope that makes sense. Make sure I didn't unplug my thing. Nope, I'm still working. We're still good. Okay, so once you got everything loaded, then it's important you look at these two things right here. Your corruptions, this is the number of bytes that the corruptor will corrupt within the file, within your ROM. The higher this is, the more difficult it's going to be to create something interesting. So for example, we'll just put some wacky number in here. So let's put 10,000 in. Okay, we'll just set this to 1 for now. Well, this is just going to be for informative purposes. So, as you can see, you may get something on the screen, but your game's not going to start. And this is 10,000 corruptions. You're never going to get anything. So this is the result. If you put your number too high, you're going to get stuff like this where your game won't even start. Now, this is where the Q-Learning will come in, because you'll be able to do more bytes. And I'm going to show you at least one training method of how to do that. I'm actually surprised that we're getting anything on the screen here. That's interesting. So as you can see, you'll get nothing. But if you put like some low number, like 5 for example, you'll get the game, it'll run almost perfectly normally. So here's Star Fox. This is what you'd normally expect. And as you can see, there's nothing kind of out of whack, right? You know, and if you want to play Star Fox, that's fine, but we're not playing this to play the normal game Star Fox, right? We're actually wanting to create something interesting. So what you want to do is you want to have some balance here. So like 150, and we'll go over what these contestants mean here in a second. But if you corrupt 150 bytes, this is about, well, you'll see. You should see something interesting. It crashed here. You know, that's not what we want right there. So we can actually train this. Getting a bad couple here. It's been working quite a bit with this. Okay, here we go. So as you can see, we didn't get the Nintendo logo. The Star Fox logo is out of whack. You don't see the spinning plane. So as you can see, creating something interesting, but not crashing at the beginning. Okay, so this is where I normally train it right here. We'll go over this here in a second. But I just want to get my one training example in before we do. So this is as far as I normally train. Now there's not a lot interesting happening, but it's not crashing, so we're gonna go ahead and set that. So let's go over more of this. So before we do that, if you ever have an interesting corruption and you want to corrupt off of that, this is where branch comes into play. So hopefully I haven't created any bugs. I haven't. So what will happen with branch is you go into your folder here under branches, and as you can see, here's B0. It'll automatically create this file within your branches. It'll be identical to your corruption. So if you put this in its own unique folder, or even, I believe it will work even if you have it in your branches, but it'll work off of the old Q tables. But I haven't tested this code. It could crash, and I may even get rid of branches by the time this is done. But I think it's a little bit of an interesting feature. So if it's there, that's why it's there. But if you ever do create a branch and I still have that feature, my recommendation is you put the branch in its own folder so it acts like its own standalone game, right? Because while the Q tables will work off of the regular Star Fox code, there's no guarantees it's going to work off of your off of the corruption in itself, if that makes any sense. So I just figured I'd go over that. We go over our branches. Now, I've been switching this around. What is contestants? What does this number mean? This is where the magic of the machine learning works. Because every time you run this corruption, and we'll run another one here. We'll go through this one actually. So we're running through our training example, and we got a soft lock here because it's not letting us advance. So what you do is you hit Alt-Tab, you go back to your program. I don't have a better way of doing this right now, so you just have to Alt-Tab. You make sure that you tab over to the corrupt button, because that's where I have the button event. And then what you do is you hit 1 if it did what you wanted, and then you hit 2 on your keyboard if it didn't do what you wanted. So we got a crash. Crashes are not fun, so we're going to hit 2. And so what happens when we hit 2 is it closes this out, and then it runs everything through. And then it runs everything through what's called Q tables. Now, all these Q tables are just a list of weights and values. So what it's going to do is it's going to look through every byte you have corrupted here. So, for example, we're corrupting 150 bytes. So what it's going to do is it's going to look through every single byte and then which Q tables are associated with that byte. So if we go into our Q table here, Q table 0, this is our most fundamental one. So it's going to go through here and it's going to look for the number associated with the byte that we corrupt. Now, numbers themselves aren't important, right? So all these numbers, don't let them confuse you, because you don't ever need to know what they mean. All you need to know is what the program is looking for. So it's going to look for the byte that was corrupted. So say it's this byte right here. And then what it's going to do is it's going to look at this value right here, and then it's going to modify it. So for example, we hit 2 because it crashed our game, right? So this naughty byte right here will get it'll be more toward 1 if it's a bad byte, if it creates an error, if it creates a crash, or whatever you may not want. You could train it for anything. But whenever you hit 2, all these bytes are going to go closer to 1, according to the learning rate, and we'll go over that here in a second. But all you need to know is, for now, is when you hit 2, it will go toward 1. And so, you know, it's going to go through all these tables, and it'll usually go through multiple. And I don't think it's as important to know what these mean. I may go over this later on. Well, I could go ahead and go over it, actually. Like the tech is based on the divisor of the address. So, for example, for table 0 here, this is the address of the byte in decimal that we're altering. So all it's doing is saying, where in the file is the byte that we just altered that crashed our game? And then it's going to give that a negative reward, or a punishment, if you will. It's going to give it a higher cost. That's what we typically refer to it as, or a higher error. So it's going to look for that. That's just the raw address, this table 0 here. And then what I have is I have an array of divisors. So for example, this is technically, this is the address, so this is just a divisor of 1. So this is like the address divided by 1, right? And then this is divided by 2, 3, 4, 6, 12, 16, 24, 32, etc. You know, the numbers aren't hugely important, but you know, what's important is, why are we using divisors, and what does it do, first of all? So, for example, let's just say we corrupt something at, like, the 10,000th byte in the file. So what this will do is, this says, okay, at byte number 10,000, you know, what is that byte? And what is the current value, and then did it crash our game or did it not? It says it crashed our game. You know, we're giving it the negative reward. Okay, now this is a divisor of 2. So what happens is, okay, what is this address divided by 2? Rounded down, right? So if we get an odd number, we just round down on anything. So, you know, you divide that by 2, and then this will be divided by 3, this will be divided by 4. And the reason why we do that is a lot of things within, like, ROMs, like, you'll often see the same 3 or 4 byte addresses, right? Or the same 3 or 4 bytes repeating. And it's important that we understand which section of the file we're talking about. So it's more like sectioning something off. So, you know, let's just say we have 1 million bytes in a file. That's about what Star Fox is, 1 million bytes. So this will just be 1 million. So this one will just be 1 million values because it's just, we're just using the address. This will be 500,000 values. This will be 333,000 values. So a third of the file. And then this will be 250,000. And sectioning it off like this actually helps for when it encounters something it hasn't seen. So in terms of the number of things that this thing can corrupt, you have about 1 million bytes times 32 different types of corruptions that could be done to it. Because we're corrupting in a certain way where we're not able to corrupt, we're not able to turn every byte into every other byte. You know, a lot of that's not important. A lot of this is just the technical kind of stuff. But, yeah. I think we'll just leave it there, though. But it's just important to realize that these are just sectioning off the file. And what happens is, if it hasn't seen the byte, then it's going to go through all of these until it kind of has a value that it has seen. And I did not go over that very well, but it's not that important that you understand this. What's more important is that you just understand the concept of what it's doing. So it's going through all those Q tables and it's editing them. And then when it goes back through to corrupt the files, what it's going to do is it's going to go through those Q tables. And so this is 1333. It's going to go through 1333 bytes, and for each of these 150, it's going to select the best one. So, for example, it'll go through byte 1, and then it'll randomly select 1333 bytes. It'll look up which of those bytes has the lowest number in whatever Q table it can find it in first. Right? So first it looks in this main one to see, because this is the fundamental one. This is the byte that it's editing plus the corruption that it's giving it. So, you know, byte number 10,000 equals 243. That would be a corruption that this is looking for, right? So, but if it can't find it there, and it usually can't, because there's about 32 million bytes, or 32 million different things that it can corrupt. So a great deal of the time it's not going to find it here. So it's going to look through there, then it's going to look through here, 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 and it's going to look until it finds something that it can associate the value with. And so the end result is basically, the higher this number is, the better chance it's going to find something that works. Right? So for example, you know, we've been using 150, right? And it's been doing good. So what happens if we just turn this to 1? What if we just say, we're not going to select among any bytes. We're just going to randomly pick 150 bytes to corrupt. So what happens when we do that? We're not going to get many that work. We may get some. Like, see, this one's a title crash. Let's see, this one's a title crash. You know, you may get like 5% of these that work. We may get lucky and find 1 or 2 if we keep going here, because 150 is not a huge number. But as you can see, it's working a lot less than with that, right? So we just tried 5 bytes there. Now let's crank this up to 100,000. Maybe 10,000. We don't want it to take too long. So if we crank that up to 10,000, it's going to take a while to load each thing, because at that point we're looking through 15 million bytes. Now, as you can see, this will work every time. Virtually every time. So let's look through here. And I can almost guarantee you almost all of these will work. Now see, this is the only important thing to know, is that this is how it learns. We actually got kind of an interesting one right there because our plane just flew off into the distance. Okay, so let's try one more just to kind of show you that this does learn. And I've only trained this for about maybe a half hour in preparation for this. So as you can see, it's worked virtually every time, right? So the higher you set this to, the more often you're going to get something that works. And often the higher you can set this to. Now, of course, the trade-off, like I said, is number one, the higher you set this to, the longer it's going to take. And so, when you're corrupting, basically what you want to do is you want to find a value that works where it's not going to take more than 5 seconds for you to load your corruptions. Because if you're having to recover from crashes and you're having to re-corrupt everything, it can take a while. So, but there's an important thing to realize. Like, if you multiply this by this, you get what's called the search space. This is just the total number of bytes that it's going to look through. And more or less, if you just multiply these together to get a constant thing, you'll be able to maximize your efficiency of how many contestants you have and how many corruptions you have. So for example, I like to use a search space of 2 million. I have a Ryzen 7 processor, so my processor is a little bit on the high end. It's like above average, but you may not have that kind of processor. So, you know, you may want to use a lower number. And for smaller games like this one, like 1 million, I like to use a search space of 200,000, which is what I usually use for Star Fox specifically. Because if you go too high, it could be too good at finding stuff and it'll just search for the same thing. So for example, like this 10,000 and this 150. Very often, when you have this kind of configuration, you're just going to get the same bytes being loaded over and over because it's going to be too good. It's not going to learn. You want something low enough where it'll learn fast, but you don't want it to learn too much. And it's just something you'll have to take by feel. So what this is 200,000 right here, 1333 times 150. And so, yeah, what you do is that. So if you want to do this search space, let's say you don't want to do 150. Let's say you don't, like I usually start off at 20. And so for 20, you'd have, I believe, 10,000. Yeah, 10,000. So you'd have 10,000 contestants. And this will learn those 20 bytes really, really quickly. In fact, mine is basically where it's almost perfectly learned, right? So, before we get to the training methods and what these alphas here are, just a couple of little notes. This selection type here is an outdated feature, and I'm going to be removing it as soon as I feel comfortable and ease of mind doing it. So that'll be gone. Table lock, if you just want to use the values as they are, but you don't want your program to learn. Let's say you feel like your program is producing amazing stuff on your corruptor, and you don't want the learning to screw it up, or you don't want to make a mistake yourself and throw things out of balance. What you do is you click this, it will not learn. It'll use what it's learned, but it won't learn. And then you have what's called clean copy here. All clean copy does, this is mostly, for example, if you want to create a save state on your emulator, right? This will create, it'll create a copy of your ROM, but it won't do any corruptions to it. So basically, if you click clean copy, then all you got to do here is you just go there, you go to save state. You don't have to worry about the game corrupting your save immediately. You just go, you create your save state, or maybe you want to get to a certain part of the game before you start corrupting, and then you load your state. You do it that way too, right? So this just makes sure that there's nothing corrupted. You know, you could also, you know, set the corruptions to 0 too, you know, but this is just something you could turn on, turn off as you need. Now these numbers up here, these are just for analytics. The analytics suite might be a little more complex by the time this comes out, or this might be what it looks like. All this is just a little helper function. So this is just gonna, like, each time you load up a session, it's gonna average out your positive and negative rewards that you give it. So like when you hit 1 or you hit 2 on your keyboard, when you alt tab like we were talking about before, you know, the more times you give it a positive reward, this percentage will go up. The total is just the number of attempts. So, you know, this is just to make sure that, like, you know, for example, you know, if you're wanting to see what percentage of success it is after 50 attempts, you know, you kind of keep track of that. Your average weight is probably your most important feature right here, because this is basically how well it's learned the table. So let's go back to our 150, because we'll learn a little bit live here. And then we'll go 1333 like we were at. So we create something. And so let's just run through this once. We'll run through our training. You know, so like I said, I like to go through my training is I go through all these title screens. And then, you know, we get the orbiting planet, and then we get the radio message. And then once we get to the tunnel is when I say it's done enough to show that this is pretty cool. See, it's done. This is what it's kind of learned how to do for me. It learns kind of to go backwards. You know, this is the kind of stuff that your program will learn. And because I have the divisors, it's been really learning how to... Yeah, this is cool too, where it gives you the from below view. You don't normally see that kind of view, right? So, you know, this is a whacked out camera view, right? So this isn't soft lock, this is just the camera screwing up. That's always interesting. But, okay, so, you know, it gave us all we wanted. So this average weight right here is 18.1%. What this means is that the average of everything that it looked at. So, you know, it goes through 1,333 of these for each of the 150, and then this is the average that it was able to find. And that's important because the lower this is, the amount that it's learned how to produce corruptions that do what you want. Right? The closer to 0 that is, the better. And one important thing too is if you take this number and then you double it, so we get 36% roughly, and then you take 36% of 150, that's about the percentage of bytes this is learned. This is going to learn for each attempt. So, for example, you know, we got about, we'll just call it 40% of 150. So we're learning about 60 bytes per positive attempt. And what determines the learning are these alpha values. Now these will probably be changed. I'm probably going to change this to learning rate or reinforcement. Positive and negative reinforcement might be good names because alpha is more of a technical academic term. You know, and you guys want to have fun with this, right? This isn't just a research project, right? This is an actual program. These alphas, or these reinforcement rates, are how quickly your program learns, right? So minus alpha just means when you get a negative result, when you hit 2 on the keyboard, right? You hit 1 for the positive and you hit 2 for the negative, right? So you hit 2 when you're crashing the game. When the game crashes, you get a result you don't like. You hit 2. Okay, this is that learning rate, right? And so what this means is values closer to 1 means it's going to immediately learn that value as well. So for example, if you have a negative learning rate of 1, that means it's going to immediately say that value is the worst, do not use that. Right? It's going to maximize how horrible that value is. The positive alpha would do that, but for positive outcomes. Like, this byte is great. There is nothing better than this byte. We're going to set it to no cost, and we're going to leave it at that. Now, these will usually be set to the recommended values. You could kind of play around a lot with these. You can, you know, maybe set your positive alpha to slightly less, or you can even set it, you can even reverse these if you want. But there is a logic behind having a positive alpha of near 1 and a negative alpha that's very small, right? But that's important to know. So the lower the value is, the slower it will learn. And the more it will retain what it previously knew about the byte. So for example, let's consider the positive result. Say you have byte number 10,000 that we were talking about. Okay? Your ROM loads byte number 10,000, it produces a positive result. Right? So it's important to note all bytes start at 0.5 because it's about a 50% chance. We don't know if that byte's going to be good or bad. All we know is that this byte is something we have not seen before, right? So if we hit 1 on our keyboard at that point, having this value at 1 means it'll go from 0.5 to 0 because it's going to completely learn that this byte is a good, perfect byte that no matter what, we're going to use and is never going to crash. Right? Okay, but let's say that happens. We have byte number 10,000 goes from 0.5, it produces a positive result, so therefore the tables change it to from 0.5 to 0. Because again, the byte is perfect, and 0 means perfectly good, no cost, no error. 1 means horrible, bad, never does anything good for us. Don't ever use it. Right? So it changes this to 1, but what happens if we load that same byte? Let's just say I were to click this corrupt button after we just hit that, and then we get a negative result. Because that'll happen, because you'll have good bytes mixed in with bad bytes. And the good bytes will just get caught in the way. You know, those bad, evil bytes, they're the ones that cause the problem. Right? Because remember, we're loading 150 bytes here. So, not all of those are going to be good. In fact, usually, only a couple of them will be bad. And so what happens then? Well, this is where the negative alpha comes into play. So, what this will be is, okay, so we got this byte number 10,000's now at 0. That's what we've established. So, what negative alpha will do is, instead of setting it to 1, it'll remember that it was 0 before, but it'll give it a very, very small penalty here. So, it'll just go to 0.00664, as you see here, right? So just forget those other zeros, and in fact, I might even get rid of these trailing zeros sometime, I'm not sure, but it's important, you know, it's going to be set from 0 to 0.00664, so it's only going to give a small negative. Now if we set this to 1, so if we were to go like that, and set both positive and negative to 1, what would happen is, it would go from 0 to 1. So this right here would just be binary. Like, it would just be, we encounter a bad byte, we're just going to set it to 1, we'll never use it. We encounter a good byte, we set it to 0, and then we always use it whenever we encounter it. So, you can do that, and you may even have faster results total by doing it. You may actually get a file that learns within a couple minutes doing that. But the problem is, the problem that you're going to face if you do it that way is, because most of the bytes are going to be good, you're going to end up with a program that's going to lean to be incredibly conservative. So those bytes that never fail will become more and more prevalent, and then you just won't get anything interesting happening. Right? So this is why you want to have a small error rate for your negative attempts, because most of the bytes are going to be good. And here's why you want to have the positive for that. It's like, there's a million ways things can go wrong, right? There's like, you know, 1 or 2 bytes can be bad, but if every byte is producing something positive, you want to have this overwhelming positive reward, because you have everything that you know works right in front of you. So you produce a good corruption, you know that's a good corruption, right? There's no uncertainty, there's nothing that you have to retain about anything bad that's happened in the past. It just works. That usually works in general as a rule of thumb. There's certain kinds of things, and I'm probably going to add more tools as we go. There's a couple more tools I may want to add that probably aren't even on this, and that'll probably just require another update. But, and we'll go over those drawbacks if I ever have those tools. But in general, you want to have an overwhelming positive reward and a small negative reward. And you may and you may even be thinking, well, why not have the negative reward at 0? Because, you know, that's what I would sometimes think about. And the reason why is because if you encounter a byte for the first time and it fails, you want your program to kind of lean away from using it if it's possible, right? So, as I say, all bytes start at 0.5. You don't know if they're going to be good or bad. But if the first time you edit a byte is bad, you want to have that slight negative so that it can differentiate the bad, like the ones that have loaded, that have produced bad results, and the ones that have produced bad results, and you want to differentiate them from the new bytes that you initially load that you don't know about. So you'd rather, if you're looking at bytes, like just think of it as a human being, right? You know, if you're looking at bytes within a file, you'd rather select an unknown byte that you've never seen and chance that it's going to crash your program than load a byte that you may have only seen once but crash your program, if that intuition makes any sense. So, you know, and also there's the idea of having a byte that worked once but then very rarely works after. You want to have an escalating negative for that byte, right? You know, so, you know, if something succeeds the first time you see it, you get your value of 0, and then it fails your next 10 times, right? You want to have this small negative alpha right here, this negative reinforcement, so that it's going to be less and less likely to select that byte in the future. And this is kind of where having a positive alpha of purely +1, it's a little bit of a drawback because it doesn't remember the negative errors, right? You know, so there's like an argument that you may want to have this extremely close to, but not quite 1. But if you look at the math of how it works out, if you're loading anything like above 5 or 10 contestants, let's just say the math is going to work out where the chances of a false positive are like virtually nothing, to say the least. So, you know, in general, this is just this is one training exercise that works. You have a very small negative alpha. You have a positive alpha that's either 1 or, in the very least, very close to 1. Right? But there's one more thing before we kind of go over a little bit more about the training method that I use. And that is, these numbers aren't absolute. So, for example, your positive and your negative alpha that you have here, right? That applies to this main Q table. So all these values here, your values are going to apply in an absolute way to. And this is the tool that I might add later on for people to kind of customize a little bit, is like everything after that. Like, for example, the program will first look through this Q table and see if it can find the corruption that it randomly looked for. See if it's seen it before. If it can't find it, it's going to start looking through the addresses and then these divisor tables that we've set up here. So, again, as we went over before, this is just the address. This isn't like the value that we've assigned This is where in the file we've corrupted, right? In other words, a divisor of 1. And what it is I'm not going to go over the exact formula, but as the divisors get larger, the impacts will get the values of your positive and negative here will be multiplied to be smaller and smaller. So for example, here's our divisor Q table number 0. This is our address. Now, a lot of these actually have low values because it's only dividing by, like, basically by a half, like by 2. So you're still able to get, you don't see any zeros here. So for example, in this one, in our main, you look here, there's a lot of zeros, and all these zeros mean is that these are the values that it's found that's worked, right? And if you look at these very small ones, these are ones that have worked and then they didn't work. So for example, here's actually, well, this is probably from when I did out of 20, but in general, all these zeros are ones that have been found to work. And all the very low but not quite zeros are ones that have worked, and then again, it didn't work because it probably was combined with something else that's bad. Right? But, you know, the important thing to realize is there's a lot of zeros here. Here you have a lot of low numbers, but you don't have zeros because it's just dividing by 2. So for example, you know, we get a positive result here. Instead of having an alpha of 1, meaning it either sets the value to 1 or sets the value to 0. In the positive alpha, it always set it to 0. It divides it by 2, basically. So each byte starts off as 0.5, right? And most of these have been hit more than once, but in general, you'd see a lot of like stuff like near 0.25, 0.3. Here's a 0.17, and then these which have been found to work consistently, you'll be like 0.06, 0.05, stuff like that. But you see a lot of stuff that's low but not 0. But let's kind of go lower on here, and as you can see, there's a lot of like 0.49s. In fact, everything here is 0.9 for some weird reason. And then here, the same thing. You get a lot of stuff that's near 0.5, right? So, you know, and then here you have a lot of 0.47s and 0.48s. So as you get kind of higher up on this list, or the lower numbers, so there's so here will be 12, and so as you can see, the higher up you go, the little bit more of an impact it has. And all this means is that as we get down, it learns a lot slower, because what happens is, like, when you get down to 31, there's only 15, because we're dividing by a very, very, very high number. And we've only got about 1 million bytes. So this one is 65,536. And you're dividing 1 million by that, so you're getting about 15. Right? But you're also saying that it has almost no impact. And in fact, actually, if you go through, if you were to actually... and be a little hard to demonstrate this in a way you understand. There's some of the code, but you know, the bottom line is, like, these tables that are way down are almost never going to be used. In fact, really, I'd say below anything below 12 is going to very seldom be used, because there's going to be already values associated with it. But really, none of that's important. What's important to realize is that these values are not absolute of all the tables here, just this main one. Because it's not always going to find the exact corruption. It's got to actually look through. You know, and that's just basically some food for thought. So, training method. Now, what you generally want to do is, it's going to depend on what you're trying to corrupt. So, for example, on Star Fox, generally you want to look for something. You want to look for a number of bytes that's going to get you about a 35% success rate. And I won't be able to do that here because I've already got this trained quite a bit. But you want to start with basically some number of bytes. So for Star Fox, about 20 to 30 bytes is good. I usually start with 20, right? And what you want to do is you want to figure out the search space that we were talking about earlier, the amount that your PC can handle, or the amount that's kind of comparable to your game. So for Star Fox, we decided we're going to use a search space of 200,000. So you want these things to multiply by 200,000. So you take your number of bytes. So we decided 20, right? So you just take your search space, 200,000, divided by your number of bytes, and then this is the number of contestants you'll have. So, you know, we decided we're going to do 20 bytes to start. And then we're going to have a search space of 10,000. Okay, and then what you generally want to do with your minus alpha is you could do one of two things. You don't have to do this exact, because all that really numbers for your minus alpha, all that really matters is that it's pretty small. But what I like to do is you go to an equation solver here, and you want to solve for what I like to call the optimal amount of error, right? And you can copy this equation. You don't need to. You could even replace 1 over e with something. But 1 over e, what's important about that is if you're looking at the total error rate, the number of times that your program will fail, you're going to want to have that failure rate be very close to 1 over e. So all this is doing is saying, you know, where is that point on this equation? So what you want to do, though, is you want to look for because we said we was going to do 20 bytes. So you just kind of want to keep plugging in values here until you get to about 20 bytes. So we're at 0.95, and this is about 20 bytes, right? We could probably go 0.951 or 952. You know, I think 0.951 would be fine, or, you know, you could even just do 0.95. We'll just do 0.95 because that's what I normally use anyhow. So, and then that's what you're going to set your error rate to right here. 1 minus this. So whatever difference between 1 and the number you arrive at is here. And as you can see, I'm using Math Papa, so you should be able to copy this exactly. Well, we want to go 0.05, not 0.95. Because again, we're looking for the difference between this and 1. Right? So 1 minus this will give you your ideal error rate. Now, I'm not even sure if this is the exact thing, but like I said, like, all that's important is that your negative alpha is small. I just do this because it's more of an evolution off of my other methods, and you can look at my first video to look at my old method. You may be able to kind of get a little bit more intuition as to why I'm structuring my math in this specific way. All I know is, number one, it works, and number two, it probably doesn't matter, because honestly, I don't always change my negative alpha. Like I said, it just matters mainly that it's a very small number. That it's a small enough number where you're not going to be intermingling a lot with unknown values, or, you know, it's not going to produce so much of an error that it's going to throw away stuff that's good. Because if you set this too high, like, you know, let's just say we set this to like 0.25, what'll happen is you'll have something good come off of this. So for example, you know, you have a really kick-ass corruption. It does everything you want, and then you give it a positive reward. You know, you push 1 on your keyboard, and then it loads something else. And let's just say it loads that byte, and then you give it a negative reward. And then it loads that same byte, and then you give it another negative reward because some other byte crashed the program. You've basically completely eliminated your kick-ass corruption just because you've set your negative error rate at too high. So that's why you want to have it small. You want to have it small so to be cautious with stuff that it's seen occasionally do a bad thing. But it's not going to completely remove it from the equation. Right? So that's why you want to have this low. Right? You can even set this probably very low. You know, and just all that matters is, you know, and then one other thing, a little bit of intuition too, is you want to have this set to low, but you also want to reduce it when you're increasing the number of corruptions here, just because it's naturally going to increase the level of difficulty per byte of producing something that's not going to crash the game, or that's going to be interesting, or whatever you're trying to train it to do. So that would be another important thing, is punish it less if it's trying to corrupt more stuff. And that's basically generally what this is doing. Is, like, for example, this is set to, the ideal here is 20. X is equal to 20. But if we were to set this for 0.99, right? This means that we want to set it so that the ideal, that at 33% success, it's going to be 0.99 per byte. 99% per byte. Right? That'll get us to about 100 corruptions. So, according to our little formula here, we'd set this to 100, and then we'd set this to 2,000. Right? And you know, this part right here, like how we arrive at that, that's probably, you know, like I said, like, just in general, just understand that the higher this number is, the more skilled you're expecting your program to be. You know, so for, you know, at first, your program is going to load up a lot of errors. You know, and I may do a live stream of a session of training of this, you know. But I just more want to try to get the intuitions as best as I can. I'm not the world's best person at explaining, but hopefully I've been able to impart some knowledge about this program to people who may be using this someday. So, anyhow, that's all I have for now. Oh, one more thing. If you're ever wanting to, so for example, if you change your values here, and then you just want to work off of a new sample, you just click reset. All your numbers are reset. All your average weights, your averages, that'll be completely reset to nothing. It's like resetting a calculator. And then you just work off of that, do your corruptions, do your training, whatever. So, again, this is going to probably be gone. These are probably going to be changed. I'm probably going to make these regular text boxes with an alphanumeric filter so that people don't import letters and shit on here. There may be a couple more tools. There may be an analytics suite. We're going to go over anything that changes, but I just want this here for documentation's sake. Anyhow, thank you guys for listening. God bless, and I'll see you all in the next video.